A very good evening, Doctor. This is group 53, ML 53, evening. Presenting to you Lendshield AI, a dual module machine learning framework for credit risk assessment in Uganda's savings and credit corporations. We are
two members.
Mogisa Joseph and Long Nachamba de Mariam.
Great introduction. So, of our preparator. So, we are having credit management in Uganda remaining as a challenge because of the institutions not receiving services from the credit bureau. So, over the 2,000 institutions that are available do not receive those services, and they operate at a power of 15 to 25%. All those ones are the results of decision making, manual decision making, non-data driven decision makings. So we progress through the introduction. So as I said, we have over 2,000 circles and 200 microfinance institutions in Uganda, and managing a lot of money, but then operating at very high portfolio at risk percentage. And so that's where we come up with Lendshield AI, which we are going to present through this paper. Lendshield is a dual module where we have built in taking an approach of two modules. So module one, which is an application gatekeeper, used in pre-disbursement when the loan is going to be taken out. And then module two is loan monitor, which is used to monitor the loans as they are running, open loans. So we shall look at what we mean by monitoring open loans next as we go. So we look at the background and the education review. So a lot of work has been done also in this area. So we have classical credit scoring and its limitations in the current market. In the Western world, a lot of work has been done in this area, but then using logistic regressions, but they work well with bureau data, and therefore we find that those modules do not perform well in areas like the Western Sahara, where like the data collection and management is not good in those institutions, and that's where Uganda falls. And that's what gives us the need to build these modules. So we have graduate boosted machines, how they perform on tabular predict data. So they also have their limitations that have been tested, but they have limitations of, we can say, they have limitations of overfitting, data leakages, if not carefully handled. And those are the areas we try to address. We look at how we split our data, and we look at how to eliminate data leakages to ensure that these modules are giving us accurate results. So we shall progress through
the computational problem statements. So here, basically, we are looking at what are we going to curb? Which problem are we going to curb? And the study mitigates minority class collapse and a transidative institutional leakage. Basically, here we have the what question. It asks us that what are we going to do? What are we going to deal with? And we are going to look at the input geometry, which consists of over 20,000 loan records, and they're exhibiting a severe it's a ratio of 4:3:1 class imbalance, and 16.73% is a best default rate, and profound heterogeneity across data sources, including an 82 100% accounting inconsistencies among the highest volume circles. And then the symptoms in this, we saw that when the supervised classifiers are trained naively or on such imbalanced and structurally disparate corpora, they frequently exhibit severe metric illusion. Therefore, the model devolves into a majority class predictor, achieving an artificial 83.83% accuracy while missing 100% of actual defaults. Yeah. So it's imbalanced. Then we have the why and the why. Here it basically optimizes the failure, like the occurrences in the coordinates. Then we have the solution. Most likely here, the computational architecture must strictly enforce an imbalance aware out of the distribution learning regime. And this necessitates the application of pipeline isolated, the smart oversampling, and strictly confined to the training manifold to prevent generative leakage. The performance will be strictly evaluated, and then the naive aggregate accuracy thereafter. Then I'll also talk about the data set. We are describing the data set and the OOD data discipline. So our data set is the raw data temp.csv, as it's indicated that we are covering over 20,000 loan records and 73 variables and 23 variables from multiple Ugandan circles. Here, as you can see, we have the group, the category, we have the key variables. Because of time, I'm not going through them in details, but then I'll take you through the computational breakdown. The leakage hazard. If the model sees even a few records from a specific sample during training, it will cheat. And then the group shuffle split solution. This one just ensures the model is tested on entirely new circles and it has never encountered before. And then the pipelines mode, it applies mode only to the training data and it prevents generative leakage.
Look at the exploratory data analysis. So we structured our analysis across 5 dimensions. So we have the target variables, data quality. Those are the summaries. So, so the target variables, how do we look at checking the imbalance available there? And we had to carry out some visualizations, and we came out with that findings that we have 16% default rate. So that is giving us a 4.3 to 1 ratio. So that is the 16%, then the rest are fully paid, like the ones who never defaulted. So we got that through visualization, and therefore we have modeling decisions that we carried out. So we have data quality assessment. We carried out these visualizations and came out with findings of the null volumes and then we had to carry out some modeling decision. So just to look at this, so we looked at Fisher target relationships, where we revealed the strong monetary effect. So whereby like we found first loan borrowers default a lot, and then we looked at borrowers who have come for several times. We looked at from first to around 6, whereby we saw the rates are falling greatly. So we shall take through the slides whereby we carried out some of those visualizations. The first one, we can look at the class imbalance. This is where we visualized statistically. We looked at fully paid. You can look at the green bars. There are more. And then those who never paid past maturity. So the red bars giving us a very low bar. So we progress. This is where we looked at data quality. the Nile columns. And then in our visualization, we didn't just visualize, but rather we had, when we visualize, we have to get key findings, and then those key findings directed us to modeling decisions, which we had here, like columns which are completely null. And these were effects of some of them, the data extraction process, the pipeline we built to mine the data. Some of them failed, so we had full and null columns which were not helping us, and we had to drop them. So we had visualization to look at the multicollinear. So we look at how features are related to each other, and therefore we had to group features together. These ones which are grouped, they are showing us that these features are overlapping, and therefore they're just going to cause noise. So we had to make decisions to drop some of them. So like you find a feature has been represented through another one. So we can be like let's say we can say interest paid is already represented in the total amount paid. So we just progress. So so we can look at another sample of visualization. It will just pass through the visualizations quickly. So we can look at the geographic and the business risks. So so the key findings. So we have like Gulu City, they're having 78% default rate. So it is 4 times greater than the national average. And then therefore we come out with a modeling decision. We say we have to encode the district, because we look at there is an impact of a borrower coming from a district whereby different borrowers from different districts have different defaulting rates. So yeah, those are the visualizations we made, and there are a lot more, but because of time, we shall just head back to the paper write-up. Just wanted to give an overview. So the likes of temporal and geographical patterns, we looked at them, whereby we found things like January disbursements, they are defaulting a lot. So we looked at the month and therefore had to identify January and February, and we look at in Uganda, so those are school fees months. So what did we come out with? We had to label, we had to scale, and then we have school fees month. So to help our modules run, and we have good accuracy. So this is just the summary of the key findings and then the modeling decisions. So it's the summary of everything that we have. So if we look at the feature engineering, so
In the feature engineering, here we just had to categorize the findings, and we categorized them in only 4 tiers, but the fifth tier was explicitly enumerated. And this table shows the strong predictors, like the cores which we used to predict, and the strong predictors included loan duration, then the days, and the loan account. As you can see, this is the first tier, the second tier. Yeah, and the medium predictors, the engineered features, the data quality flags, and the debt leakage. As you can see here, the raw feature space is reduced from 73 to approximately 50 usable variables. All these columns here were dropped as we confirmed by the EDA. They were dropped, and they followed the rule from module 1 training, which shows that they were permitted in module 2, where a repayment history is available by design. And the high cardinality categorical variables, business type, the district, and circle, were initially encoded using global statistics computed before splitting. In the pre-computed encodings. The circle performed using the group shuffle split kid on circle. And as we continue with
so we are just out of time with that, but we shall wrap up a little bit. So methodology. So we followed a two-module approach whereby we have module one and the module two. So module one, we said, is the application gatekeeper, which is for pre-disbursement. And so, so this module was evaluated across 5 machine learning architectures. So, so spanning the interoperability capacity spectrum. So these modules, we happen to discuss them and look at how they function, their architectures throughout. So, and then when we evaluated this module across 5 architectures, so we had to devise a mechanism of selecting the best module. So what can I say about this module? So we use the threshold approach whereby we discussed this down this side, but I will wrap them up because of time. So we used threshold tuning, and then we had to base on our policy in order to come out with the best model. So what was our policy? We used F2 score, whereby recall is going to weigh double than precision. Why? Because in finance, one of the policy is we better catch defaulters, and we better catch the defaulters, other than just identifying that this one will repay. So we take much attention on catching defaulters than missing them, because missing defaulters will cost us. So that's why our fine tuning was aiming at achieving the best F2 score. So, and then another basis we used to come out with the best module for our module one was that another approach that we used was that the stability across different circles, and that brings us to the concept of robustness of threshold tuning there we discuss. So it brings us the concept of robustness across circles. So that's where we used the let's say I talked about circle robustness. So getting diverted by some noise. So another approach we used to select that was the so robustness across circles. So we are going to look at stability. So what is the stability of that particular model? So we try under different thresholds. So then we evaluate and validate what is the gap when we do different multiple splittings. How is this module performing? Because in each splitting, we get different sets of circles in the bonding, in the validation set. So, and then we train it, we keep recording, and then we get the standard deviation and mean of all those metrics. So then when we get the mean, the one that has the smallest deviation, and that is the most stable module. So it brings per circle stability and robustness. So that means even if a new circle comes, the module is not basically just relying on a given circle pattern. It's not just performing well on a particular circle, but rather it can try to generalize and perform well on different circles. So because of time matters, we have a lot of validation, cross circle stabilities, and a lot. But then we also discuss the multi-tiered error taxonomy, the explainability concepts, whereby we don't just make the yes or true or false, but rather we enhance our model using SHARP. I could be using SHARP, which uses the principles of gaming, whereby the features are the players and the final scorers rewards are their contributions to the decision. So we use that to explain the decision to the loan officers. So it's not just in black box for them. So we go ahead and discuss the deployments due to time factor. And we discuss how we shall move our MVP to up to a complete product. So we have our commercial model there. Then conclusion, we look in the next steps I've discussed. We shall continue to collect the data for those which were null, data which will enable us to improve our accuracy. Because as per now, after auditing, we didn't discuss auditing, but the work is there written. After auditing and the removing data leakages and ensuring proper splitting, the stability, our accuracy has fallen. We have good F2 score, but not the best. So we aim at collecting more data, which can help improve our accuracy, re-engineer them again. And then we hope to follow the appropriate step to appropriate and legal step to get the module to full feature. So the request to stop there. Thank you.